Hey, this is Presh Towalker. In this video, I will present 6 impossible puzzles with outside-the-box solutions. How many can you solve? Puzzle 1. Here is a maze. You have to go from start to end. But there is a rule. You cannot pass through the same color door 2 times in a row. That is, you have to alternate between blue and red doors. Can you figure it out? Now, if you're having trouble solving this puzzle, I want to give you a big hint. You can go through the same door or enter the same room more than once. The only stipulation in the puzzle is you have to alternate between doors of different colors. So how can you do it? Rather than just show you the solution, I want to show you how you can solve the solution by thinking through it logically. So here's a general approach. Let's start out by considering each different area as a different room. So at the very beginning, we are starting out. So let's call this room number 1. We enter the first area and we'll call that room number 2. We can call this area room 3. Let's call this area room 4. This room 5, this room 6, here we have room 7, and finally, when we exit, that can be one more room, which we will call 8. So we have 8 different areas of this maze. So how do we get from 1 to 8? We need to pass through different colored doors. So let's connect the rooms by the doors that are between the 2 rooms. So when we go from the starting point to the beginning of the maze, we're going from room 1 to 2, and we have to pass through a blue door. So we will connect 1 and 2 with a blue colored edge. Where can we go from room 2? We could go to room 6 by passing through a blue door. But we can also go to room 6 by passing through a red door. We can also go to room 3 by passing through a red door. Where can we go from room 3? We could go to room 6 through a red door, or we could go to room 4 through a blue door. From room 4, we can stay in the same room by passing through a red door. This is an important piece of the puzzle. We can also go to room 5 by passing through a blue door, or we could go to room 7 by passing through a blue door. From 5, we can go to room 6 by passing through a red door. Notice there are 2 red doors, but I will just leave one edge because we can go from 5 to 6 going through either one of the red doors. We could also go to room 6 by passing through a blue door. And from room 6, we can go to room 7 by passing through a red door, or we can exit the maze by passing through a red door. That'll be to room 8. So now let's just focus on this graph that we have created. Our goal is to create a path that goes from room 1 to room 8, and as we pass through another room, we have to alternate edge colors. Now, instead of trying to work from room 1 to room 8 by going through edges of alternate colors, here's another tip. We can work smartly by solving from the end of the maze and going backwards. So let's start from room number 8. From room 8, there's only one thing we can do, which is to take a red edge to room 6. So now we are room 6, and we have taken a red edge. So, since the very last move of this puzzle, if it's solvable, is red, we need the second to last move to be a blue edge. So from room 6, we know that the second to last move has to be blue, so it cannot be red. We know that any of these red edges will not be the second to last move. So we can just get rid of all these red edges. This is going to eliminate a lot of possibilities. So we can see that from room 6, there are basically 2 places we could have come from. So one place is room 2, the other place is room 5. Now let's say that the second to last move was coming from room 5. Now what happens when we get to room 5? We've just gone through a blue edge, so now we would need a red edge. But we see there's nowhere that we could go from there. We are stuck here. There's no red edge that goes anywhere else. We've already deleted the edge that was going to 6. That'll just take us in a loop. So we know that this cannot be part of the solution. So we know this is not where you want to go. So we will delete this edge. We now see that 5 is a dead end. We will delete everything going to 5. And we can also easily see that 7 is a dead end. There's no need to go over there. And now we can see the path we need to take. Clearly, we need to go to room 2. From there, we go to room 3. Then the only choice is to go to 4. From 4, we are allowed to circle back to 4 by taking a red edge. This allows us to take a blue edge to 3. So we take a red edge to 2, allowing us to take a blue edge back to 1. So we have solved the maze in reverse. In order to work the maze the correct way, all we need to do is flip the arrows to get a path from start to end. So let's go ahead and flip all these arrows. We now have this path. We can overlay it on the original puzzle, and we will now just draw out this solution. We start in room 1, and we take a blue door to room 2, a red door to room 3, and a blue door to room 4. This is where the puzzle gets creative. We take a red door to stay in room 4, which will then allow us to take a blue door to room 3, a red door to room 2. Finally, we take the blue door from 2 to 6. Now we've entered 6 with the blue door, so we can exit 6 from a red door, which takes us to the end. Congratulations! We have solved the puzzle. What an amazing solution! Puzzle 2. A library bookshelf has several volumes of an encyclopedia of mathematics shelved side to side as shown. The pages of each volume are 3 centimeters thick, and each cover, front and back, is 0.3 centimeters thick. Assume the same dimensions for all of these volumes. Now, there is a bookworm in the library because nobody is checking out an encyclopedia of mathematics, and a bookworm has gnawed, perpendicular to the pages, from the first page of volume 6 to the last page of volume 7. What is the distance of the bookworm's path? So this puzzle tricks a lot of people, and let me illustrate the wrong way that most people think about the problem at first. So we have volume 6 and 7. When most people read that you're going through the first page of volume 6 to the last page of volume 7, intuitively you're going to be traveling a distance that's almost equal to the length of the 2 volumes. But you're going to be excluding some covers. You're excluding the front cover of volume 6, but you are going through the pages of volume 6. You are then going through the back cover of volume 6 and the front cover of volume 7, and you are then going through the pages of volume 7. So most people think the answer would be something like 2p plus 2c. The pages have a thickness that are 3 centimeters thick, so p is equal to 3, and each cover, front and back, is equal to 0.3 centimeters, so c is equal to 0.3. Substitute in to this expression, and we have 2 times 3 plus 2 times 0.3, and this simplifies to be 6.6 centimeters. And that's what most people think when they read the puzzle at first. But this is incorrect. The problem is we have the totally wrong perspective on what it means to go from the first page of volume 6 to the last page of volume 7. We're usually reading books in our hands, and we don't have a clear understanding of the distances when books are put on a shelf. So what is the correct answer? We need to think about it carefully. So let's look at volume 6. The very front of the book will be on the right side, and the back of the book will be on the left side. So the book will go from right to left. So the first page of volume 6 will be right in the middle of this diagram. That will be the front of the book, and that's where the first page will be. Now let's think about the last page of volume 7. Volume 7 is also read from front to back in this manner, and the back of volume 7 is going to be right in the middle of this diagram as well. So we only need to calculate this distance from the first page of volume 6 to the last page of volume 7. So this distance will be equal to what? It will only be equal to the amount of the cover of volume 6 and the cover of volume 7. So we need to add the front cover of volume 6 and the back cover of volume 7. So this distance will be equal to c plus c, which equals 2c, and that will be equal to 2 times 0.3, which equals 0.6 centimeters. Amazing! Puzzle 3. There are 3 people in this puzzle. We have Alice, Bob, and Charlie. Each of them is a finger pointer. Alice says that Bob is lying, Bob is saying that Charlie is lying, and Charlie is saying that Alice and Bob are both lying. Logically, who is lying and who is telling the truth? Assume that each person is either a truth teller that always tells the truth, a liar that always says lies, and everyone knows each other's type. And no one is uttering a joke or a sarcastic statement because in logic puzzles, there is nothing to joke about. Let's work through it logically. Let's suppose that Alice is telling the truth. In that case, Bob is lying, which means Bob's statement that Charlie is lying is wrong. Therefore, Charlie must be telling the truth. But if Charlie is saying that Alice and Bob are lying, that contradicts the assumption that Alice is telling the truth. There is no way that Alice could be telling the truth and we don't end up with contradictory logic. This cannot be true. Now, let's consider that Charlie is telling the truth. In that case, Alice and Bob must both be lying. But then Alice's statement that Bob is lying would be a true statement, and that contradicts the fact that Alice is lying. So once again, we have a contradiction, and it's not possible that Charlie is telling the truth. So the only possibility is that Bob is telling the truth. Let's make sure there are no contradictions here. If Bob is telling the truth, Charlie's statement will necessarily be false as Bob is telling the truth. Alice saying Bob is lying will also be a false statement as Bob is telling the truth. Therefore, Bob is telling the truth and Alice and Charlie are lying. And that's the answer. Puzzle 4. We have matchsticks arranged in the shape of 5 squares in an L shape. The challenge is to move 2 sticks to make 4 identical squares. It is said that children solve this much easier than adults. So how can you figure it out? Most adults think about the problem like this. They look at the word move and they think that the word move could also be interpreted as the word remove. So they take these 2 sticks that are in the corner and they just remove these 2 sticks and they say, look, I have made 4 identical squares. I am so clever. Now this is one possible creative solution to the puzzle. However, it's not exactly what's intended because the puzzle doesn't say to remove 2 sticks, it says to move them. So let's try to rearrange the 2 sticks so that they're part of the final puzzle. So how can we move 2 sticks? We will still have a shape that uses all of these sticks, and we will make exactly 4 identical squares. Let's think about it logically. So if you have a square made out of matchsticks, you will need to use exactly 4 different sticks. Now, how many matches are in the original arrangement? Let's go ahead and quickly count up these matchsticks, and we will see that we have a total of 16 matchsticks. Now, our goal is to make 4 identical squares. If you multiply that by 4 sticks per square, that'll exactly be 16 sticks. So if we want to rearrange 16 sticks into 4 identical squares, this is only possible if each stick is on its own square. None of the squares will share a common side. Now in the original arrangement, some of the squares are clearly sharing a common side. So let's take a look at these two squares. We clearly are sharing one stick for two of these squares. So imagine we want to have 4 squares that have no common sticks. So let's say we take this square and we leave it be, and we need to somehow remove one of the matches from this square that's next to it so that we don't have 2 squares sharing a common stick. Now the same thing can be true in the bottom arrangement. Here we have 2 squares that are sharing a stick. So if we want to keep these 4 sticks to be one square, we know that we'll have to remove one of these 3 sticks and move it somewhere else in this arrangement. So now by symmetry, we can just consider pairs that are corresponding to each other. So let's get started. Suppose we take these 2 sticks. Now imagine we move them somewhere away. Is it possible that we could place them somewhere around the remaining sticks and we end up with 4 identical squares? I don't see it. So we will eliminate this possibility. Now let's look at another possibility. Let's take a look at another pair of matches that are symmetrical. So let's take a look at these 2. Let's imagine we're going to move them around somewhere else. Well, here's the arrangement that remains. I don't really see any clear way that we could put these 2 matches to get 4 identical squares. So we will eliminate this possibility as well. So that leaves only one more pair to consider. So let's take these 2 matches, which are on the middle, and let's imagine we move them out. Now we are left with exactly 3 identical squares, and there's exactly one spot where we could create a square. All we need is 2 more sticks. So voila, we go ahead and put these 2 sticks over here, and we have created 4 identical squares by moving 2 sticks. So this will be the solution. We have moved 2 sticks to create 4 identical squares. Wow. Puzzle 5. There are 3 different keys and 3 different doors with locks. Each key opens a different door. Unfortunately, the keys are mixed up, and you need to label them so that you know which key opens which door. In how many attempts, in the worst case, can you be sure you can identify all 3 keys? Let's work through this logically. Let me label the 3 keys as B, G, and Y. Let me label the 3 doors as 1, 2, and 3. So here's some notation. Suppose I write BGY. That will be a solution in which B opens door 1, G opens door 2, and Y opens door 3. So how many different possibilities are there? Well, this will exactly correspond to the number of permutations of 3 items, which is 3 factorial, which equals 3 possibilities for door 1, then 2 possibilities remaining for door 2, and 1 possibility for door 3, which will be 3 times 2 times 1, which equals 6 possibilities. Let me enumerate them. We have BGY, BYG, GBY, GYB, YBG, and YGB. Now, the amazing thing is we don't actually need to test all 6 different possibilities. The remarkable answer to this puzzle is we can identify the keys in just 3 attempts. So how can we do that? Let's suppose that we start by testing the key B on door 1. Now, we're looking for the worst possible case, so it is possible that this key does not work on door 1. So let's say that this is not going to work. So when we look at the 6 possibilities, we can eliminate the very first 2 because we know that B will not work on door 1. So now let's put this to the side and suppose that we test G on door 1. Now we're looking for the worst case, so it is possible that G also doesn't work on door 1. We can then eliminate 2 more possibilities, GBY and GYB. But now here's the interesting part. we know that B and G don't work on door 1. So we must be sure that Y will work on door 1. So we already know that Y works. We don't need to actually test it out on door 1. There are only 2 possibilities remaining, which is YBG and YGB. So we need to differentiate between those two. So let's go ahead and see whether B or G is working on door 2. So let's test B to door 2. So if we put B to door 2, suppose in the worst case that this does not work, in that case, we would know that B doesn't work for door 2, it must work for door 3, and G must work for door 2. But now we've identified which possibility works. We know it must be YGB. We have used exactly 3 tests to do this. Therefore, after 3 tests, we can be sure we have identified all 3 keys. We don't need to work through all 6 possibilities. We can have that so that we just figure it out in 3 different tests. Incredible. Puzzle 6. Here's a geometrical figure. You could call it a leaning tower. The puzzle will be to solve for the area of this square at the top of the diagram. But let me define this diagram a bit more clearly. So at the very base of this figure, we have 5 different isosceles triangles, and all of their bases are aligned. So each of these triangles is isosceles. The very bottom is the base, and we have the 2 sides that are not the base will be equal to each other. The bases have lengths of 12, 13, 14, 15, and 16 centimeters. Now, on top of these triangles, we have rhombuses, or rhombi. Now, each of these 10 different quadrilaterals is going to be a rhombus. So what exactly is a rhombus? It's a quadrilateral that has all 4 sides that are equal to each other, and it's a type of parallelogram, so opposite sides will be parallel to each other. Now, the very top rhombus is actually a special case. It's going to be a square. And the challenge is figure out the square's area. This is a truly wonderful geometry puzzle, and I admit that when I saw it, it stumped me. But when I read the solution, it was so beautiful, I just had to share it. So let's work through this problem step by step. We will start out by defining the side length of the square to be equal to x. Since we have a square, all 4 sides will have the same length. Also, all 4 angles will be right 90-degree angles. Now in a square, we have all 4 sides equal, so these 2 sides are equal. Now we have 10 different rhombi, and we know that all of the sides will have the same length, and opposite sides will be parallel. So in the square, this side will be parallel to this side. Now as we go to the next rhombus, we know that we will have the same side length for all 4 of these sides, and opposite sides will be parallel. So we can continue this to the next rhombus. We'll have the same length, and then opposite sides will be parallel, and that will continue down to one of the sides of this isosceles triangle, which is also a side of the rhombus. This length will be equal, and this side will be parallel to the opposite side. So let's take a look at this length of the square. So we can then just translate it to the opposite side of the rhombus. We know that it'll have the same length x, and it will be parallel. We translate it to the next opposite side of the next rhombus. It'll have the same length, and it will be parallel. And finally, this goes down to this side of this rhombus, which is a side of this isosceles triangle, and we know it will have the same length x. And let's just note that this yellow line segment will be parallel to this side of the square. Now let's work an adjacent side of the square. So let's mark this line segment. Now we know that opposite sides will be parallel, and all 4 sides of a rhombus will be equal to each other. So we can just translate this length to the opposite side of the rhombus. We know that we have a parallel line segment, and it will have the same length x. we continue going down this tower, and we continue to this triangle with a base of 16 centimeters, and we know that this line segment will have the same length x, and it will be parallel to this side of the square. But now, let's take a look at the two adjacent sides of the square. We have this yellow side here, and we have this orange side, and we know in a square, the two adjacent sides will meet at a right angle. They will be perpendicular to each other. So we know at the base of the diagram, this yellow line segment must be perpendicular to this orange line segment. And amazingly, that's the key detail we're going to need to solve this puzzle. So remarkably, we can actually get rid of all these intermediate edges. We can just vanish a lot of this tower. So we can go ahead and remove all of these intermediate edges of all of these rhombi. We don't need these to figure out the area of the square. And remarkably, this whole diagram is going to collapse quite incredibly. We can also get rid of these isosceles triangles in the middle. We don't need them at this point. So now let me just collapse the diagram. Let me move this right triangle and connect it to this left triangle. And we know that these two edges meet at a right angle. We need to figure out the area of the square, which will be equal to x squared. So let's do this just by looking at these two triangles. Let me just power them up and magnify them. So now we have two lengths of x that meet at a right angle, and we have two isosceles triangles. Let's drop an altitude from each of them. So let's drop an altitude from the triangle of 12 centimeters. This will divide the base in half so that it will have a right angle, and we know that each length will be equal to 6. Let's drop an altitude to the base of this other isosceles triangle. We know it'll meet at a right angle, and the base will be split in half, so we have 8. Now let's label this acute angle as blue and this acute angle as green. Now this blue plus the right angle plus this green will be equal to a straight line. So we have blue plus green plus 90 degrees is equal to 180 degrees. Subtracting 90 degrees from both sides of the equation, we have that blue plus green is equal to 90 degrees. In other words, the blue and green angles are complementary. So we have two right triangles. We know that they have complementary angles, which means they will be similar, but we know the hypotenuse has the same length. Therefore, these two right triangles will be congruent to each other. So, where we have a base of 6 here, we know that the altitude will be 8, and in the other triangle, we have a base of 8, and the altitude must be equal to 6. So we have a right triangle, and we know we can solve for the hypotenuse. We have x squared is equal to 6 squared plus 8 squared, and that is exactly equal to 36 plus 64, which equals 100. So we know the area of the square is 100 square centimeters. And like magic, we have figured out this puzzle. The area of the square is 100 square centimeters. Amazing! Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.